Obrigado. Aí eu transformo o Norberto em apresentador daqui, certo?
Perfeito.
Perfeito, obrigado. So Norberto, just to tell you, I will just introduce you, and I will give to you the word.
Okay, just talk, and then at the end, when you want, you just tell me start, and I will do it. Okay. Give me the time to, of course, to share the screen, but I will be okay. You must give me the possibility to share the screen.
Yeah, there is a fun stuff working over here because
at the moment I cannot share the screen. At some point, you must give me the possibility. Okay.
Great, that's okay. So let's thank you everybody that's coming, and now you are pleased to have Professor Norberto with us. Norberto Masciocchi is a co-founder of To.Sca.Lab. It's one of initiatives to deal with the total scattering in the new the technology and research fields as nanotechnology and so on, material science. And Professor Norberto has a large contribution on education, and we have the pleasure to have Professor Norberto from 2014 and 3 times until now. We were co-organizing a school, a Latin American school here at Florianopolis. So Professor Norberto Masciocchi, there is a large scientific contribution, and he has a lot of opportunities also, and he works at the IBM at the 18s, and there's a large experience working with the pharmaceutical industries and different industries around the world. His scores, it's impressive, you can see, and there's a lot of information that the people are seeing us could achieve looking at the internet and at the websites. And just one more thing that I would like to say, introducing Professor Masciocchi, it's that we do an effort in UFSC, Universidade Federal de Santa Catarina. There is a cooperation with the Universidade de Studi de Insubria, and so we're still running this cooperation. So the students are invited to visit and to take part of this. You are always welcome to give opportunities to students that live and study here at the university to visit Como. Como, it's this city at the north of Italy. It's a side of one of Meso's most famous lakes in Europe. It's a border of Switzerland, and something that for sure Professor will give you some slides that he just prepared. So I finished with my introduction. I thank you very much, Norberto, and I'm very pleased to see you again, and hope in the near future you are again together taking a caipirinha at the beach. And so please, very welcome, and I will give you now the tools to start your presentation. Maybe Antonio could help me and transform Professor Norberto as a presenter. Could you give some clicks, Antonio? Let's see. Oh, yes. Norberto, it's up to you. Thank you very much. I'll just turn off my camera and see you later.
Okay. Okay, first of all, thank you everybody for being here today and to listen to my seminar. And I will basically introduce a number of basics at the beginning and slowly proceed towards newer science. I try now to share my screen, and hopefully it will work. Okay, it will take some time before it loads. Can you please tell me if the screen is seen? I don't hear anybody. Can you please tell me that everything is okay?
It's okay. It's running. We can see your first slide, Norberto. Thank you.
Okay, perfect, very much. Okay. So this talk will start with a very brief introduction. A brief introduction will be a virtual tour of where I'm talking to you today. I am located in Como, a town which is near the star up there, very close to the Central Europe, to the mountains, to Switzerland. You see, it's very peripheric site in Italy, but it's a very beautiful area. As you can see from the picture I've taken from our lake, this is a town, not a big one, just all present on lake and hills. And if you look at the farther image, this is a town from the other side in a beautiful sunny day like today. Okay, so just going to the major part of my talk, I will start with a reference from the book by Francesco Maria Gribaldi. If you can see, this was published in 1665. It means something like 350 years ago. And in this book, there is a sentence on top on the right, which says proposition 1, sentence number 1, which I will try to show in a more detailed way. So this is in Latin, and says that light propagates and diffuses not only directly, not only by refraction, not only by reflection, but also in a new, strange fourth mode, which is called diffraction. So we are talking about diffraction today, and this is the first time where in history, diffraction was coded into a title, into a text, and so on. So we are not talking about anything new, but something which was already discovered 350 years ago. But science has born modern science about that time. It took several years before physicists developed a theory of scattering. And so in this slide, I will present something which is about 50 years of physics history. So interaction radiation matters, which comes when an X-ray photon, a high-energy photon, meets an electron. So you can see from the light, from a light here, an undulatory curve, which has an electromagnetic field. We're looking now at electric field only. When this field hits an electron, of course, the field attracts or repels the electron, depending if it's on the crest or on the hole of the wave, and the electron starts jumping up and down. So the wave comes and the electron sees the wave and goes up and down. An accelerated charged particles emits radiation. It emits radiation in the forward direction, here to the right, and the backward direction, not perpendicular. So this was the first finding was ever done in the beginning of the last century. There is a theory, that the Stanton scattering theory, which uses some vectorial properties, says that if you have an impinging beam on an electron diffuses around itself an amplitude, and this amplitude is related to the original amplitude. So the intensity which is impinging is linearly related to the scattering intensity. But there are other terms. One is this term to the right, which is trigonometric terms, which is related to the 2 theta scattering angle. One is r square, which is a distance at which one observes the material. So basically, if you go far away, the light becomes dimmer and dimmer. But then you have a term which is squared, which contains only fundamental terms in physics. Q is a charge, electronic charge. Mass is a rest mass. C square is a square of a light velocity. So this number is a fixed number. It's a very small number indeed. So that means that the scattering intensity is much smaller than the incoming intensity, because there is this term which is below 1, r square is certainly larger, and also this term is very small. One thing to notice is that if you have no charges, so if a particle is not charged, if you have a neutron here, then the intensity is automatically 0. X-ray scattering do not diffract with nuclei, so the nuclei are silent. But matter contains not only electrons, but also protons, and protons have the same charge, or the nuclei have charges larger than electrons. So here the Q square can be higher than for electrons. It doesn't matter if it's minus Q or plus Q because it is squared, but the mass of a proton, of a nucleus, is much higher than that of electrons. And then it's even squared. So it means that also nuclei are silent, and not only because of charges, because of neutrons, but because of masses. So what is happening normally is that only the electron density is seen by X-rays, and the scattering factor, or the so-called contribution to scattering to a single wave, is called the atomic scattering factor, which is related to the electron density of the atom. Is a Fourier transform of the density of the atom. This is related to the intensity which can be observed. So the larger the electron density, the larger will be the scattering by an atom. So hydrogen atoms will scatter much less than uranium atoms. So the idea is that when you have an incident beam, as you look at the panel here at the bottom, you have an incident beam hits a full atom. The full atom is silent for the protons, for the nuclei, and sees an electron. The scattering X-rays depend on how many electrons are there and where they are. The point is that how can we see where the electrons are? This is a probabilistic effect, and it's known from quantum mechanics that there is a wave function and the density of probability, which can be described mathematically. So for a spherical atom, the atomic scattering factor can be computed from quantum mechanics. So we are now in 1930s when the first wave function were computed. And as you can see here, depending on the angle, here there is reported sin theta over lambda, but it's basically a function of theta. The farther away from the zero angle, which is the direction of intention beam, you have less contribution. So if you go at high angle, you have no contribution to scattering. That's why scattering is normally measured in a small range of theta angle and not too high. This is a difference with neutrons, where neutrons are point scatterers, and normally you have this curve. We are not falling down, but are continuously constant. As you can see here, bromine minus, iron 2 plus, calcium 2 plus. These are elements or ions with different quantity of electrons, and these scale up with electrons. Because intensity goes with the square of this factor, you can see that 1 times 1 of hydrogen compares, for example, to bromine, which is 35 by 35, which is about 1000. That means the scattering of hydrogen is nearly negligible in the presence of heavy atoms. That's why it's normally said that hydrogen atoms cannot be easily seen by X-rays. Now we just make an experiment, a computational experiment, and we take a benzene ring with carbon atoms at every corner. We forget for the moment the hydrogens, and then we say, can we expect scattering from a single molecule of this? There are techniques I will show you later which can predict what the scattering of a single gas molecule is, and if you have the scattering angle here at the abscissa, then you expect that the scattering of this single molecule is a very fast decaying curve with some small bumps at higher angles. If I include in my panel a magnification of this plot, you can see that these bumps are present, are visible, and these are what are called the structure factor of benzene. That means it's a fingerprint of a single molecule of benzene in scattering space, what is called a reciprocal space. So in principle, if you have a single molecule of benzene or a collection of individual molecules, say gas or benzene, you should expect a case like this, a very poorly informative trace. If you take another organic molecule, this is a drug called vinpocetine, and you compute what the scattering should be, again you have a very fast decaying plot. Possibly you see a small bump here, which is illustrated in the insert, and the second one at higher angle, but again, it's very poorly informative plot. So the reason for this is that these are molecules in gas phase. When they are ordered within a very periodic system, here we have a nanocrystal of materials. That means that a sequence of 5 by 5 by 5 unit cells, a very tiny crystal of vinpocetine, you can see that the same molecule arranged periodically gives a trace which has peaks and valleys. So this trace is much more informative because contains fringes or some information which was not observed here. So the fact that the materials are crystallized in a periodic order gives you some enhancement of few peaks and depression or other ones, and these peaks are informative of the content of molecular shape and arrangement of this material. We'll come back later to this, but if you take now a larger crystal, not a non-crystal, larger crystal, then you can see, and I go back and forth here, that these peaks become sharper, they are more or less located in the same position, and they emerge very clearly from a background. So the crystal is an amplifier of a signal and gives you specific position where there are some geometric relation and phase relation between the different waves arising out of it. Now we go back 20 years, from the 1930s we go to 1912. In the first panel left, you see a few spots like the Dirky Fingerprints, and this was the first diffraction image ever measured by Max von Laue and his students. And he learned that these spots were not random and then could be optimized by using a better experiment. And just a few months later, these 2 months later, the same material was exposed to X-rays and gave very nice tiny spots, ordered and symmetrically arranged. So it means that this is a renaissance of a new technique, the diffraction technique, which was mentioned by Grimaldi in 1665 and was experimentally detected. This guy, but not his students, got the Nobel Prize and developed basically a technique of shining X-ray beam on a crystal, and then you see spots on the screen, exactly how you see here. Now the problem comes, how do we interpret these spots? Which kind of information can we take? So the experiment you see here, you have a source, a crystal, which is acting as a lens, and this on the screen is nothing else than the Fourier transform of the position of the atoms in the crystal. So what you observe here is something which is at the scale, laboratory scale level, a few centimeters, a few decimeters, and you image something which is down to the angstrom or nanometer range. So this picture will then soon be interpreted. So 1 year later, Bragg's father and Bragg's son, the two got the Nobel Prize because they published a paper in which, using the images they could get from sodium chloride and developing some theory which is the peak position were related to dispacing, that means informational metrics of a system. And the peak intensity is related to some formula which is structure factor formula to the position of the atoms X, Y, Z, and the nature Fj. By not entering now the theory, by using these two expression, they were able to detect the first structure ever found in the history. So sodium chloride, they could measure where the sodium are, where the chloride is, the coordination, the distances, and the size of a unit cell, which is a periodic building block in 3 dimensions. This was the first paper which illustrated this discovery. Soon after, that means July 30, only 34 days after the first paper, a second paper came out, which is the structured diamond. So they discovered a tool for which, observing spots on a screen, they could get information on size, shape, and the crystallochemical nature of any principal crystal aggregate. So in 2 months, they published the first 2 structures, and since then, more than 1 million crystal structures have been discovered, not by the Braggs, of course, but everywhere in the world. So the technique is a really powerful one, and it is nowadays used in many laboratories, which is a technique which is called single crystal technique. But what we want to talk today is not single crystal technique, which are widely available, but what we can do with powders. What is a powder? A powder is nothing else than a crystal which is broken down in many tiny particles, or a crystal which is never grown, and you obtain it from precipitation of powder from, for example, a drug when you prepare a chemical reaction. Again, we must go back to the idea of shining an X-ray source on a single crystal, and the theory built by Ewald says that is a so-called reciprocal lattice connected to the real lattice, which is somewhat the condition for having the reflection. So the idea is that when you have a point on this so-called Eva sphere, then automatically you will have a X-ray light scattering. So for example, if you take this point and you see it's nearly on a surface, you have light shining in this direction. And so this spot is created automatically by the positioning of the sample. But there are only few spots. There's another one down here, another one down here, which are on this condition. And so that means if you take a single crystal, you may usually observe only a few spots, not enough information. But if you rotate the crystal, you see the crystal rotating in the center, automatically also what is called the reciprocal lattice starts rotating. And so you put into condition of reflection many other points which are entering, exiting the Eva sphere, and then by rotating them, you have the appearance of many points on the screen, and you can basically sample all the points in your space, and all points all together make the ingredients to solve the structure and determine the structure. So having all the points measured allows you to detect the symmetry of the system, the size of the unit cell, and the position of the atom. To do this, you have to rotate the sample. Now we make a very bad experiment. You crush the single crystal into many, many tiny pieces. So basically, you obtain a powder of misoriented crystals. Every single tiny piece was originated from a single crystal, so itself is a smaller but still ordered crystal. When you have a collection of these crystals which are oriented in all direction, you lose information of this vector R star, which is indicated in red, but instead you maintain the length of this. You're normally orienting all the crystals in no direction, and all points which are from the same distance from the origin is kept at the exiting point from X-ray source towards the detector, then all these four lines you can see have the same distance. So even if only one or two of them were originally on the surface, where of a single crystal, more appear which are not on the surface, but will become on the surface when you have an orientational averaging. So all points which are lying on this circle, or in principle on the sphere in 3D, are in a diffraction condition. So now you take two spheres, it's called Eva sphere, for which you see only the circle, and you take the red sphere and you intersecate the two spheres. What are the ensemble of points in which the two spheres coincides? Exactly on this circle. So the two spheres define a circle. It's a rim of a torus. And then all the points which are lying there are in reflection condition. It means that you have a cone of rays which comes out from the center of your sample. So not only with a single crystal you have spots, but when you crush a single crystal into small pieces, the spots are misoriented in an azimuthal orientation, and then for every distance from the center you have different rings. So the idea is that from a single crystal you have spots in space. From a single crystal to the right you have spots with the red ones, but then you average them out circularly. It's like making a hole in the center and having the red points rotate all around this axis, and then you have a set of circles. And this set of circle is redundant because every point here at the bottom is equal to the one at the top, equal to the left. So it's necessary only to make one sampling from a center to any direction, to a cut, basically. If you make it horizontally, if you make it vertically, if you make it in any other direction, these give you equal information. And then you can measure what its intensity is from the center to higher angle, because remember, if this is a screen position perpendicular to your beam, then the farther you go, the higher is the angle you measure. And so this is a real picture. This is a real picture of a powder. On the left, you have a single crystal. On the right, you have a powder. You can see that the rings in the powder are not complete. For example, the center rings has some failures here there, so the intensity is smaller. The second ring has smaller intensity than the right side, so that means that this is not so ideal, meaning the orientation of the crystallite is not so random, but there are some preferential orientation. This is something one should avoid. The rings idea should be equal in intensity and equal in distance from the center, so that any cut you make in any direction gives you the same powder pattern. So the powder pattern is then something which is intensity over the diffraction angle, 2 theta, and if you take the blue one, this is an observed powder pattern which has peaks and valleys. Then you have a background which is simulated here as a green curve. This can come from an X-ray beam, they can come from the presence of amorphous material, they can come from the sample holder. Once you subtract probably background, you have a full trace, which is the black one here, down here, the tiny peaks and larger ones, which is the fingerprint of your material. Now we have seen that we have pointed out to some important issue in developing physics. Now we go what happened to crystallography. 200 years ago, the crystallographer was a mountaineer going to the fields, to the mountain, and seeking for something which was beautiful and of size of centimeter to 10 centimeter. Slowly, people learned that there are tools, simple tools. Galileo made the first microscope or telescope, but the idea is the same, and you can look deeper into materials and you can see the beauty of snowflakes, which are sub-micrometer crystals. Then, soon after, in the 20th century, electron microscope gave you the possibility of imaging directly system down to 100 nanometer sizes, so you can see these crystals at the microscope, visually, basically, with your eyes. And then, in the last 20 years, power diffraction made it possible to determine the structure of some molecular compounds. What you see down here is one of the triglycerol derivatives, which is probably clogging the blood vessel of many people. It's a very dangerous molecule, but the structure of molecules of this size can be determined nowadays by power diffraction. One step beyond, this is the instrument where we perform most of our experiments. This is a synchrotron in Switzerland. We are just on the border to Switzerland. This is 3 hours away from Como. And this is not a Starship, is a synchrotron, very similar to the one which is present in Campinas in Florianopolis, or other ways, in Campinas in Rio, or São Paulo, somewhere north of Florianopolis, and in other places in the world, mostly in the northern hemisphere. So you've seen already that the power diffraction gives you a sequence of peaks overlaid on a background. Why the peaks are there and why do you have this intensity? The peak position give you unit cell symmetry and size, so independently on the intensity which you measure at any peak position. The peak position are labeled here down with some peaks which are easily detected by carefully searching the presence of relative maxima in the power diffraction pattern. So you have a unit cell which repeats throughout the crystal, but what is the content of this cell? What are the atoms? How does the molecule look like? So this is matrix geometry, and you want to have knowledge of structure. So the structure is something which fills the unit cell, and this is encoded into peak intensity. So two unit cells which are equal but with different structural content give position which are the same angles but intensity which are different. So the intensity contains the atomic distribution in a cell, that is the electronic density in a unit cell. Then peaks are not very sharp, can be wide, can have tails and so on, or misplacement. This is called peak shape analysis or microstructure analysis, and give information about non-ideal system. So a structure, a crystal structure, ideally an infinite structure, but crystals are smaller than infinite, and if they are smaller than 1 micron, they show up in broadening of this peak. Particularly if you have also mosaicity, that means that the unit cells are not that well aligned inside the crystal, then you have fiber bonding, and so there are effects called strain, stress, and other properties which are important in the metallurgical fields. Again, I show you that here there is a trace which was set below the major peaks. This is the background. The background can depend on diffuse scattering. We will come back later what diffuse scattering is. Can be given by the sample holder, can be given by the matrix where the material is encoded, can be given by amorphous phases, or simply by misalignment of the instrument, or some ambiguous intensity which comes from other portion of the diffractometer and not directly from the sample. So the traditional application of powder diffraction are many. One of them is fingerprinting. Fingerprinting means recognizing easily one person at the customs when you enter a country. Everybody has a different fingerprint. The same happens to different crystal phases. So if you take here this material, which is called the bupropion, it's anti-smoke drug, there are several phases of this material. Only one is marketed, and the other one are fake in the sense that they are not admitted by Food and Drug Administration. How can you check if a drug is correct or counterfeited? You can just run X-ray powder diffraction. This X-ray powder diffraction can take 20 minutes. There are many custom services around the world who do this for you and check whether goods entering your country are the real one or not. And then you can see that the two X-ray traces are completely different. So that means that one is the one which is possibly allowed in the pad, another one is not. So you can easily detect this for any material which is crystalline material which comes into goods into country or to the market. Then you can also think, once you have recognized what is in our material, can we detect how much of this material is present? For example, what you see down here is an example I normally do with students a third-year course. I take a commercial drug which is called in Italy Alka-Seltzer and is used for anti-acid in the stomach when you have eaten too much. And then if you run the spectrum, you see different peaks. It is known that Alka-Seltzer contains aspirin and citric acid. I can also see that the major part is hydrocarbonate. So this anti-acid is not acetic acid. It only gives you a nice flavor. Aspirin because it allows you to keep away your headache. And the anti-acid is nothing else than hydrocarbonate, which is reacting with your hydrogen protons in your stomach. So you can say that if you do this, you measure this material in an hour, then within 10 minutes you can get information about the content and see whether the lot of production of your material is confirmed, or you have to change it because the production in this case by buyer has been wrong. Traditional application. One of the outcome of the analysis you can do is measure the peak position accurately, and the peak position gives information about the distances in the material, and the distances normally depend on the material nature. For example, if you take magnetic nanoparticles, iron oxide, you can an iron plus have iron 2 in a different ratio, and the ratio between the two is highly dependent on the aerial exposure, on the temperature, on the storage conditions, and so on. Here you have a plot where many determinations done from 1962 up to 2009 are plotted, and if you take all the determination, the unit cell is plotted on the left versus the percentage of iron 2 and iron 3. Of course, there are some scattering. This is also given by the fact that people work on different instruments, on different times and different methods. And you can draw a line which tells you that if you measure some cell parameter, then you can measure analytically the percentage iron 1 or 3. This correlation is not that good because you see that there are some scattered and some outliers. So some years ago, we decided to prepare nanoparticles with 30 different methods, and these are the 30 blue dots there, compared to the other ones, all the other colors and the shapes are from different workers. You can see that if you add all together the data, you can make a straight line, which is a red one. But if you take only those who are prepared deliberately and measured on synchronous radiation, these are the blue ones, then you have straight lines, which is still very good and even better, and is slightly shifted away. So you can just have a very accurate determination by just measuring the lattice constant, and the calibration line is different, so you have a different results from good calibration. Then I say that you can have also microstructure analysis, which is studying the shape of peaks instead of the intensity, study how the peak intensity is distributed around a single lattice node, but they're not discussing this. This is more on a metallurgical field. Something else you can do in the lab, and you can see here a custom-made system where you have some cables, some water inlets, some power supplies, and you have the possibility of heating in air one sample. And by putting one material in your pedal, then you measure it at room temperature, and you increase, say, by 10 degrees every time, every 10 minutes the temperature, and you have a sequence of spectrum. What you see in the right is a two-dimensional plot of a blue trace up there. This is the room temperature and the heating of this material. This heating provides at some point an intermediate position where one material transforms into another one. This is a quantitative conversion of a butanol solvate of this azelastine, which is the drug you see down there, into the hydrochloride where butanol is lost. So basically, you can detect the solvent domination. You can also detect the presence of contaminants, because one contaminant can melt before the other, the human material. So some peaks will soon disappear, or the contaminant is melting at higher temperature. So your peaks are disappearing before those contaminants. So this also can be a way to have a qualitative analysis of your solid material. You can detect phase transition, where you have solid-to-solid phase transition, polymorphic phase transition, which are not seen if you dissolve them into solution to obtain a normal chemical analysis. And you can also measure the thermal expansion coefficient down to very tiny values, 10 to the minus 5 coefficients. So what we have seen now, in the first slide, we have seen Lau and Bragg. They developed a theory for single crystal data based on this function you see there. This is a structure factor function. It's possible to use well-crystallized sample, and you get as an output structure solution and detailed stereochemical description. These techniques was soon adopted in the 1960, late 1960 or 1970 by Ritfield, who used the Bragg theory and adopted to a different formulation, where the experimental data are not anymore integrated intensity of individual reflection, but it's a total pattern intensity of overlap Bragg reflection. So this is adopted from powders, from single crystal you go to powders. This is normally used for real materials when you have solid reaction, thermal treatment, and so on, where single crystal are not available. And this, of course, can give you the possibility of solve the structure and describe in an approximate way the stereochemistry of your system. Approximate means that there are still some uncertainties, but as I always say, that little information is better than no information at all. This meaning that if you do not have a single crystal and you have only powders, then you can get some information which sometimes is good enough for continuing your studies. And so, for example, the purity, the unit cell, the cell changing with temperature, and so on, which are available even in the absence of single crystals. There is a procedure for structure solution from powder diffraction, which is now nearly 20 years old. The procedure may change depending on the type of material you have. So it's different if you use ionic, if you use pharmaceuticals, if you use organic, if you use polymeric materials. But it's very important to know that this sequence, it's not a sequence of steps which takes you to the goal, but sometimes you must go back and several times in a feedback manner to see whether there are errors in the different steps which have led you into a close and dead end. So the powder diffraction is still a good method, but needs some external knowledge and some good skills to get the information of structure from the power diffraction data. The Ritval method, which I mentioned before, uses a complex function, and the important thing is that within this fk square, this is a square of a structure factor here, this is a structure information. Everything else is a metric information, which is where the position of the pixel and background all together in a different complex system. So there are many factors which are to be refined. These are instrumental parameters which are zero shift, the sample displacement. Sometimes you can also refine a wavelength, the polarization coefficient, and background coefficient, which are somewhat unknown, and you may use polynomial, you may use Gaussian, and so on. Then you may have cell parameters. These are metrical cell parameters. Then you have structure parameters. The structure parameters are the same you find in single crystal analysis. Atomic coordinates, cytocopus factor, thermal parameters, sometimes the atomic scattering factor, which are for absorption. You have profile parameters, the shape of the profile, which you cannot eliminate. You have the anisotropic peak shape and width, that means some peaks are narrow, some peaks are broader, and then other correction factors. So this is a list of parameters which can be easily more than 50 parameters. So that means you have to find the minimum of one function, the best agreement, searching and spanning a hyperspace of 51 parameters, 50 independent parameters, and the one is your best matching. This is very formidable for a task and can be done nowadays by powerful computers. The important thing is that in a single crystal diffraction, you don't have instrumental parameters because you measure directly the intensity of each separated spot. The cell parameters are determined beforehand, are not touched anymore during refinement. The structure parameters are those of your interest, and there are no profile parameters and no other correction factors. That means that a single crystal uses a subset of parameters. Is easy from the mathematical point of view, and the number of observations is much larger because they have all independent parameters, which can only depend intensity, which can be measured. There are 10,000s of data which can be measured. So the Ritval method can give you many information. It has been used to refine approximate structural model from metals, alloys, minerals, and pionics. Nowadays, also and has given ab initio structure solution from organic material, organometallic material. You can see here a complex organometallic material which has hydrogens. The hydrogen in the presence of Arrhenium atoms cannot be seen, but if you couple simultaneously data from single crystal, easily give information on a metal atom, and from neutrons, which give information on hydrogen atom, by using simultaneously two data sets, one from X-rays and the other from neutrons, you can get the overall picture because the information is encoded partially in the synchrotron data and partially in the time of flight neutron data. So you can have here multiple dataset parametric refinement. By parametric, it means something which changes slowly. Here it's a paper in which material was heated, so the pattern number goes with the temperature. You can see that the percentage of one material versus the other one decreases, one increases, and the percentage of the green one is kept constant. It means you can study kinetics and transformation in the solid by using a heating stage and a simple single refinement where among the parameters you put the shape of this curve, and automatically you will get the position of these flexes, the height of this curve, and so on, because you use multiple data sets at the same time. Then you can also study which is called defectiveness, everything else which goes beyond the ideal crystal. We will come back later to this sample, which was published by us, and the use of Ritval method into a more advanced manner. Let me go further and see what we can do now in a third method, that is Debye approximation. My title was Bragg and Debye were right. Bragg was right, the two Braggs were right, because you see that with the formulation, more than 1 million of materials have been studied and the structure revealed, so they opened the way to a very powerful technique. Now we use a different formulation. We have an intensity. Here Q is something which is related to theta, is 4 pi over lambda sine theta, is nothing else than the translation of theta to a new variable. And this IQ is a sum of a different atom contribution, and Rij is the distance between each atom. If you think of having a small nanoparticle, it's possible that these atoms are like 1 million atoms. And you should know the position of this 1 million atom and compute all the distances. That means 1 million times 1 million, that's 10 to the 12 distances, and then make this calculation. Of course, for many years, this was impossible. Nowadays, it is possible in the most simple cases to work on the personal computer. In other cases, it's possible in more complex cases to use on a server. But this means that a new technique based on very old formula can be used. This is normally done on a so-called total pattern intensity, when you have diffuse scattering, which is scattering given by the sample, which is an idea, which is falling below and between the Bragg peaks. So it means that the background is not anymore treated as an annoying contribution, but must be interpreted on a structural basis. This is normally done for nanocrystal, for defective amorphous solids, and you will see some example on this application. To.Sca.Lab, another Nobel laureate, wrote this formula here. It's expressed instead of having Q with the proper function, Q 4 pi sine theta by lambda. This was the original function, which has been later developed by our colleague in Switzerland, the Swiss synchrotron. Instead of having I over theta, you have the orientational average of the cross-section measure over a certain scattering angle. This is equal to intensity, and is what you measure exactly. And this is given by a self-interference term. This is a sum over the atom of the square of this term. There is an O, which is this is a occupancy factor, which means that in one solid material, some sites may be vacant, and so the occupancy factor is not 1, can be 0.95, 0.9, and so on, depending on the quantity of material which is missing in that particular site. Then you have a so-called interference term. The same term you see here, but it's just summed over a couple of I and J, and then this sequence has again the structure factor of the the atomic factor of each scattering factor of the atom, a temperature factor, which is how every atom moves, and its occupancy. And here you have again Q. This is small q, is nothing else than 2 pi sine theta by lambda, and the distance between the two atoms. So this is a reformulation, which also has included recently a description originally set by Barry but never used for computing because these Bessel functions are difficult to compute manually. In 1952, there were no computer doing this. So the two equations here have now been merged and can give you also the possibility of computing what is called the Debye scatter equation for a texture sample. That means a sample which is not orientationally accurate. That means that it's giving arcs and not rings if you just have the two-dimensional X-ray power picture. Again, we go to the initial sample, but now we just look at the sample in different manner. We have benzene. Benzene is made up by 6 carbon atoms. We forget about the hydrogen, and every carbon atom has a few neighbors. Every carbon atom sees itself. So 6 carbon atoms have 6 distances of equal 0 value. And you don't see it here, but there is a number 6 in this plot. This is called GDR, or the paired differential function. There are 6 distances at 0 distance. Every atom sees itself at 0 distance. Then every atom sees 2 atoms at distance of 1 length, of 1 edge of this here. So how many edges do we have here? You have 6 edges. That means that, again, the second peak, which is some distance between the shorter distance, 1.39 angstrom in benzene, 6 distance all equal. Then every atom sees also an atom at a larger distance, which is the chord taken up here. And again, there are 6 chords. And then there are only 3 distances, which is the para position or 1,4 position of benzene, which is 1 here, which is 3 distances here. So forgetting about the self-interaction term, which is the distance of one atom from itself, you have 6 by 6 times 6, plus 6 plus 3, 15 distances. Originally, you have 6 atom times 6 minus 1 times 5 divided by 2. Again, we have 30 distances, which are counted twice because one atom sees each other also in a reverse manner. These 15 distances are then fed to a computational system and gives you exactly what you've seen before. So the plot we've seen before was computed by the histogram of distances which you compute from a small model. Now we take vinpositin. It's a very complex molecule, it's an organic molecule. Then you have distances which are short, this carbon hydrogen, there are short, some other which are medium, the carbon nitrogen, some longer, the carbon hydrogen. And then also you have non-bonded distance, which are somewhat longer. If you just compute all the distances here and you make a histogram, you have this kind of bump. Beyond a certain value, you have no distances, that means you have no longer distances than extension of this molecule, and you have a maximum intermediate value of distances. These peaks you see here are those who give information on the structure. It's not a flat curve, it's not a smooth curve, it's a curve which has a few peaks. These peaks translate themselves into the curve we've seen before. Again, if I do the same computation from an order system, a larger system, the plot of the distance in the histogram plot shifts much to the right because you have a larger system. And again, some peaks here are not just noise, are the structure information that some peaks occur much more frequently than others. And they are translated by the Debye equation into a scattering pattern. Unfortunately, this is not what we normally measure. This we measure the scattering pattern, and we would like to not to compute the scattering pattern from a model, but retrieve the model, so the red line, from the scattering pattern. This is the called pair distribution function approach, which from experimental data here the right tries to obtain this information. As you can imagine, the details of this information are very tiny, so very difficult to obtain this. While the one-way direction, which is build a model and compute the pattern, is much more straightforward. So you have collected a data set, then you build a model, you can compute this histogram of data and transform it with the Debye equation into the model pattern, and you can compare the model pattern with the real one. So the feedback is continuous if the model pattern doesn't match the real one. If yes, you're finished. If not, try to modify your model until you get a better convergence. Now we just see again what the difference between Bragg scattering and diffuse scattering is. Let's imagine you're having a tiny unit cell, a single unit cell of titanium dioxide in the rutile approximation. Then if you have this structure and you compute the scattering factor of a few atoms here, you have something we've seen before, a very poor information system. Now you take this cube and you make it larger. Instead of having 1 by 1 cube, you make it 2 by 2, 5 by 5, and 10 by 10. And so you just move along the diagonal of this plot, and you can see that the bigger the cube, the more definite are the peaks. And so when you reach 10 or 100 or 1000 cells altogether, the peaks are very narrow. So they're going from the left bottom to the top right, in diagonal you have an increase of size. Increase of size is equal in no direction. Now let's make an increase of size which is only along one direction. You take one little cube and you stack many cubes on top. For example, what you see here, this tetragonal prism is nothing else than a crystal made, a rod crystal made by 10 cubes on top of each other, you see that the trace you have here at the bottom is slightly different from the one on the top, in that one peak here is very sharp. This peak becomes sharper as long as you increase the size along C. That means that this peak is strictly related to this growth direction. And the measure of this peak gives information about the C-axis. Now we go in a different direction. We take this crystal, we make slabs which are 10 by 10 by 1 or 5 by 5 by 1 and so on. Again, you have an increase of a number of peaks, but you have other peaks which come out. These peaks come out because you are increasing coherence in the AB plane and not along C. Note that the peak which was emerging up here in the 1 by 10 system is here missing, because we are not elongating along C, but we are elongating along AB. So that means that if you have one of these patterns, you can easily distinguish the size and shape of your system. So the size and shape of your single crystal, once you get a sample of single crystal in a powder, can be easily retrieved by this plot. Unfortunately, this is normally called Bragg peaks because you have no background, and this is called diffuse scattering. But it's nothing else than the same effect. This is a small nanoparticle, this is a larger nanoparticle of a single crystal. So what is normally called Bragg peaks is the total scattering with very little diffuse scattering. When you talk diffuse scattering, it's nothing else than total scattering, where the diffuse scattering or the background is wider or bigger or larger in intensity than the Bragg peaks. But everything is encoded in this so-called total scattering method, where the total scattering includes both Bragg peaks and both diffuse scattering. So there is no distinction between these two different extremes. Normally, when you have an ensemble of material, you don't have crystals which are all the same size and all of the same shape. The example I give you here is that we studied in the past annotated system which have this kind of prismatic shape. The crystal you see here is 4 by 3 nanometers in width and 9.2 nanometer height, so there is an aspect ratio. This is more than twice higher in one direction. This is called 2.1 is L over T. But this is one crystal. Then you may have some which are slightly broader, some which are slightly longer, and you have a population of single crystal. How can you define a population of crystal? You must define the spread of a certain function about its average, and the spread can be different in plane or normal to it. This is a way to plot a distribution of crystal. The maximum here, that means that you can see here at the bottom, you take two lines, you have a number which reads something around 5 and a number which reads something around 10. So the maximum probability is for a crystal which is less expanded in XY and longer in C. Or you can have other cases where this kind of image is extended vertically. That means that all the crystals have about the same width but different length, or the two length and width are correlated. So these are normal outputs which can be obtained by the biscattering analysis, which we'll show later. And if it's non-dispersed, if you look at the one direction only, you have a log-normal function which is encoded in our programs. And here you see only a tiny histogram because this is a log-normal function sampled only at 3 points. This is much narrower than the other ones here, so that this explains why this kind of flame is narrower in a horizontal direction and larger in a vertical one. So these are just sections of this bilog-normal system. And one thing I want to show is that the log-normal function can be used in two different ways. The one in number and the one in mass. The normal in mass means that you just assume that you have measured data by scattering techniques, and you may get information such as distribution. You can see them here in red. If you use the same material and you go at a transmission electron microscope and count the size of a different sample, you end up with a different distribution. In fact, this distribution represents the same material, the one only is count how many particles have a certain shape, and the other one is how many particles have a certain mass. And because the mass goes to the square, not to the cube of a size, there is a shift to higher angle, to higher value for log mass. If you take the same sample at the 10, you can get a number which is the distribution in number of 15, the average 15 nanometers, and the width of distribution 8 nanometers, the very same material obtained by X-ray power diffraction gives you 32 nanometers and 17 nanometers. But these two curves are mathematically possible to interconvert. So the information you get from X-ray is giving correct numbers. The one from TM gives the correct numbers, but you should know that the correct numbers are associated to counting or to weighing, which is different in the two cases. Only if the two systems are highly model dispersed, then the two curves are nearly coinciding. The program we used was developed in the last 12 years by a group originally at the Institute of Crystallography in Bari and at the Synchrotron in Switzerland. It's called Debussy, which is the Debye user system. It's kept on being updated, and there is a new issue every other year. Normally, these new releases are presented at dedicated summer school. One of them was in Florianopolis a few years ago. We had 3 of them in Como in the last 5 years, and the next one will be probably held, if COVID admits it, in Granada, in Spain, in September. At that place, we will release this, and we will update also the SourceForge.net, where you can download even now the latest version for running on your PCs, Macs, or Unix system. So what does modeling in Debussy does? You just take a sequence of dots. These are the definition of the origin of a unit cell of your system. Let's imagine now we have a sphere of a circle, and we define dots which are representing the shape of the crystal. Then you build on top of the crystal the cell. So you just dress the cell with the atomic content. For example, you have atoms at the center of a cell, you have atoms at the size of a cell. So you normally do nothing else than translate the single cell atom content all over your system. Of course, by doing this, you can also introduce defects. You can just cut slices away, you can just substitute atoms. It's just up to you to define what your model is. So you go from lattice nodes to nanocrystals. This is the atomic structure. The atomic structure is something which may be known from a single crystal study or power diffraction study from others. You introduce the nanocrystal size and shape not only as a circle, but for example as a sequence of spheres of different size. So you have size and shape in population. You compute within each item of the population the interatomic distances. There are some tricks which speed up the calculation called Gaussian samples. Then you calculate the DSA pattern of each crystal size. You sum up the different patterns depending on some law, for example, the log normal law distribution before, and you calculate the total DSA pattern. Now you match the total DSA pattern with the original data. There will be certainly some mismatch. You try to modify in an iterative way your parameter, for example, shrinking or enlarging the unit cell, for example, changing the number of large clusters versus small ones. So you have different model parameters, and you can just match versus the observed data. So your population are, if it's sizes only, it's small sphere, intermediate sphere, larger sphere, and so on. Could be also a small cube, a larger cube, and even larger cube, and so on, something which is monometric. If you have a system which are anisotropic, so you may have platelets, you may have rods, and you can define systems which have a certain diameter and a certain length. Then you can have cylinders, you can have prism, you can have hexagonal system, so different shapes which are fitting your data. With some external coding, you can just introduce any kind of shape you want. The shape which are now being introduced by default are the ones I just mentioned. So for every single particle, you can construct the histogram you've seen before. Here you have it separated for the first case for lead sulfide and sulfide for the lead sulfide sample we've seen before, we've seen later. And down there we have for zinc oxide, which is normally crystallizing in a Bussy type with some rod system. You have a different shape of histogram, which has a tail on the side. The tail is given by the fact that your material is not isotropic in shape but has longer direction, so there is a certain probability to have much longer distances than the shorter ones. And so these are the input distances which are used by the DSA equation. At the end of the modeling, you have data which are here in black, a computed pattern which is in green. You probably don't see the difference because they overlay very well. And the difference plot, the difference between the matched pattern and the matching one, so the calculated and observed one, is the red line you see down there. And you see the red line is nearly flat. It means that by using our parameters, and among which you have also the distribution of your sample sizes, you get a very nice fit. The fit can be then expressed in terms of this histogram, and the histogram is centered about 7.7 nanometers and has a certain width. If you compute then now the size distribution from TM, these are the materials which are given. This is a very tiny portion of our material. You can image this by TM, you can make a histogram and compute the same 7x7 nanometers system. So one main thing, why should we just go to X-ray scattering if we can just count these materials? The reasons are many. One is that who tells us that the materials in your imaging is all PBS and not something else? This is only given by X-ray power diffraction trace. The other thing is that by doing this histogram to the right, you are only having a very tiny portion of your system. You see the scale bar at the bottom is about 20 nanometers, so you are just imaging 100 by 100 nanometers. But your sample is like a few milligrams. So you are just sampling a very small portion, which has a very statistical weakness, because you're just imaging a small portion and everything else could be different. And after all, the method we are using here is very general. So the information we can extract from such a method is shown here in this hexagon. Starting from the top, you can get information on crystal shape. That's something that normally is overlooked into the normal structure refinement for single crystal powders. You can get not only the average size, which is obtained as a fallout of a refinement, but you can get size distribution not only in one direction, but in two directions. It means having the full plot of a crystal size in a two-dimensional space. You can get cell parameters and strains or modification of the cell parameter, for example, by changing the size of the material. You may have structure and distortion. You will see some example later. You can study the presence of other kinds of defectiveness, which is stacking foils, twinning, and so on. And you may have surface relaxation. That means that the surface atoms are farther away from the next neighbors than the center one. So you have a cell which is changing radially with your system. At the center, the system is much more dense than in the periphery. So this is a similar hexagon where several examples of our studies in the last 10 years are reported. You can see that this method has been adopted to photovoltaics, displays, nanocatalysis, gas storage, medicine, in the pharma and agro-food field. We have the IPATSA project we just finished, and catalysis. So you can see that there are no limits on whatsoever on the type of material. You have also here to the right molecular pharmaceutics. We have studied nanodrugs, so even organic material can be studied by this method. Now we go to the last two cases of example. This is one case where we have one of the very famous perovskite, luminescent. You see there a capillary filled by a suspension, so it's a solution containing a crystal of cesium lead bromide, which is illuminated by the normal neon light in the lab, and already by normal weak neon light shines out, emits a very bright green color. The nozzle you see in the back is the synchrotron beam, of course, in this position. Now we were taking a photo with the synchrotron beam shut, but this is a condition where we normally measure our system into capillary, in solution, suspension, so not only as dry position. So to make the story short, the perovskites are based on this kind of lead halide octahedron. And the other halide octahedra is normally described by 2-axial and 4 equatorial system, because only in the cubic phase, which happens to occur only at high temperature, all the 6 atoms are equal. If you go down to what is called the tetragonal or rhombic phases, which are obtained on cooling, there is some distortion, and then you have a clear distinction of these different halides. So our measurements were done at different temperatures. You can see, read here from 450 down to 133 in different conditions, in a colloid, as powders, or even in gel. Gel means a wet powder, so a not completely dry system. As you can see, the traces are nearly similar, but there is a portion of a spectrum which is very different. So the major difference occur in this section where this Q angle is still at the translation of the real angle, and this angle is near 5 degrees. So there are several peaks, we call superstructure peaks, which are rising from the different symmetries here. In the plot to the right, you have the observed data, which are the solid lines, and the computed data for the different structure which were observed in a passive single crystal. As you can see, when you have a cubic system, you have only 1 peak here. When you have a tetragonal system, then you have clearly 3 peaks here, 4 measured in our system. When you have orthorhombic one, the number of peaks increases and fall exactly where the peaks are observed. If you go to sodium lead chloride, apart from this tiny peak which was given by some condensation freezing water, this is ice forming on the capillary, then you see that there is no trace for the cubic system and hardly anything visible for the orthorhombic one. So here you have something visible because these peaks are very tiny, and distortion gives less information on these superstructure peaks. So that is it. Can we follow the transitions and interpret these changes by changing the temperature and conditions? So if you take now, we go to the end and we see the result. This plot is cesium lead bromide, which is simulated at high temperature using an orthorhombic system. The orthorhombic system had in this area peaks. Now they disappear. So they disappear because we have taken the original structure, orthorhombic structure, which is shown here, which is a sequence of A, B plane. You can see that every A and B plane is slightly different by the position of this chlorine in the sequence, up and down within each run, each direction. Then if you take this apart, you make a wound here, and then recombine them in a very similar manner, note that the lead atoms are equal no matter what the wound is, then you can get a slightly distorted system. It's very similar, but you have what is called the antiphase domain. You have at some point that B is followed not by A by B, and so you have stacking error here. If you have stacking error which are distributed along a certain direction, then the material is still orthorhombic but appears to be cubic. So the idea behind that is that no cubic system exists, but in nano-sized materials you have domains of orthorhombic pieces which are hinged together in a very complex puzzle. Again, you can have also different simulation. If you take a puzzle of this, these are all orthorhombic crystals, which would need to give many peaks here, and only one is given. Results in apparently cubic. So it is that in nanomaterials, you have a continuous growth of symmetry, which is only apparent. It's always orthorhombic, but the mutual rotation of subdomains and the density of subdomains changes on changing temperature. So you have dynamic operating rotation of the octahedra, which change locally the structure and make this separation higher, you have an entropy contribution, and this was in line with inelastic neutron scattering and Raman styles of similar compounds which appeared in 2016 and which were not yet understood. The last point is lead sulfide system. Lead sulfide is known to be cubic and has been cubic for 100 years. In 2012, it was proposed computationally that it should be automatically distorted into a rhomboedic phase by just elongating one of the diagonal axes. So the idea is that can we prove this by high resolution synchrotron data and our method which is capable to catch the small picometer changes position. So we have done simulation by changing this length of the vector, which means changing the angle between the three rhomboedral vectors from 60 degrees, which is the ideal one for a cubic system, to 58.6. Then we had use, of course, the size of the core and thickness of the shell. So we defined a model which is in line with the most modern interpretation of these materials. And if you look at the blue curve are for the cell volumes for different size materials. The 3.2, 5.0, 7.0 size, you see that the cell volumes are different. It means that lead sulfide has an edge length or a cell volume or a molar volume which is different depending on the size. This is given by the fact that the shell becomes more and more important when you are shrinking down the size to a small system. So the expansion of cell, which is typical for the 3.2 nanometers, the number of peaks or atoms which are in a shell compared to the ones who are in a center part becomes comparable. And then you have a definite widening of the cell volume. Then, by changing still the angle, we also measured the agreement between our data and the model. And this is measured, for example, by the chi-square. This is one of the statistical parameters which can be obtained by the Debussy analysis. You can see that all these curves, despite having the same constant cell, have minimum. The larger minimum is for the larger particles, very easily visible, but with a value which is close to 60 degrees. And remember, 60 degrees means, in this kind of deformation, ideal cubic. When you go down with the size, then you have the angle becomes smaller and smaller. That means that if you shrink the material, the deformation is higher. If you go to particles which are bigger than 10 nanometers, you probably reach a level where the cubic phase is stabilized. So that means that only at very low crystal size, stabilization of this distortion is possible. Now you take the cell volume, the cubic root of a volume, and you plot, this is basically a cell of a cubic edges, and you have three values, and the three values we have just intended to plot a curve which has this dependence. So this is the length of the quantum dots, which should be equal to a reference value modified by something which multiplies 1 over d. And this something omega is nothing else than the ratio between the surface tension and the bulk modulus. These values are, bulk modulus is known, and by doing this plot, you can see you can get surface tension value. Of course, plotting this data against three data only makes this asymptote very difficult to catch, and also if these are erratic, this curve should not fit data from other authors. We will come back to this point later. Now you can see here that the structural distortion is shifting away from the original position, from the cubic position, the lead atom, which is the most highly scattering. And you can see again that if you go to different sizes, the 3.2 nanometers is a more distorted. You have 0.12 degrees away. If you go from the intermediate one, the distortion is smaller. And if you go to the larger crystal, the distortion is less pronounced. It's only half of what is before. Again, if you go to larger nanocrystals, you have a number which approaches 0, so the structure is real cubic. What does distortion mean? It means that out of six sulfides, 3 become shorter and 3 become longer. So you have the distortion of a lead, which is becoming outside the center of symmetry and has the 6s2 lone pair, which is non-inverse lone pair, which is protruding out from a lead. Lead is not anymore a sphere. Of course, if you lose the center of symmetry, you induce the dipole moment, which was calculated for the 3.2 nanometer to be very high, 190 dBi. Is that dipole moment important? This dipole moment important is rather relevant because Murray in 2005 found that these tiny nanoparticles, if deposited on the surface, they align in tiny sequence of beads of circles, of spheres. So the spheres are not equally distributed on the surface, but try to align if they were each one a tiny magnet or tiny dipole. And this was not understood. You can see also from the figure down here that by depositing very separate VS particles, so not so dense, still you have a preference for having chains of spheres and not randomly distributed spheres. This was called the oriented attachment phenomena. It was eventually discovered and interpreted by this dipole moment. The plot you see up there is the same plot seen before after we collected data at a synchrotron, same condition, from preparation done with different methods in different laboratories by different people. And you can see that if you forget the starred ones, which are obtained by a completely different manner, by the PDF way, but not by the bioscattering fraction, so forget about the green stars, everything else falls more or less on the same line. The original line is the dashed red one. Once introducing more data than the 3 which we had before, then these all align on the same trend and the much better definition of the trend is obtained. You can also plot the alpha rhombohedral, which is far away from 60, and you can see that all these align up with the same trend, and that once you go to 12, 15 or so nanometers, then you lose information and everything goes back to 60 degrees. That means from 12 nanometers up, the system is cubic. The system is not cubic if you have very tiny nanocrystals. So this is a picture of our tiny lead sulfide deposit on the surface, on a carbon surface for TM measurement. And again, you see that they don't just arrange in a random manner, but they try to give sequences. By counting the position of this material, counting the distances, you can make easily a so-called radial distribution function. So at some distances, you have a large peak. So at 7.8 distance, you have a presence of many dots. Twice as much, you have another one, and possibly a third one here. So this is a GDR, which gives you the fact that particles are not radially distributed, but try to align. 7.8 is nothing else than the 7.7 size of the dots we've seen before. We have measured before nearly 7 nanometer size dots, and this is exactly what you observe with TM. So the final refinement looks like a normal Rietveld refinement. So you have data and model on top of each other. You don't see difference because they match very well. On the bottom here in blue, you have the trace of the solvent, which had to be collected separately because the material is suspended in solution. But one thing you can see here, at a very small angle, you have a strong peak with some variations. And if you take the small portion here, you see that these peaks have some kind of periodicity. These are so-called the pod regime of a small angle scattering measured with wide angle scattering techniques and simulated by the same Debye model we use for everything else. So the Debye scattering equation is also able to account for the small angle scattering, which is normally treated with a completely different Here you have a matching, and the matching was only possible by taking this kind of shape. It's not a spherical shape, It's not a cube, but this is so-called rhombohedron, where you have big faces, where the faces which are exposed are the 110 and not the 100 or the 111, which are typical for cubes and octahedra. Is this the correct interpretation? If we take our material and deposit them on a silicon surface and do the normal Bragg or normal power diffraction experiment, instead of having the ideal intensity, which is measured here in blue line, which matches more or less what you see here, you have extreme intensity for this peak, a much lower intensity for the second one, and altogether you have distortion of intensity. This means that your powders are not real powders, but are oriented materials, which on the surface of a silicon expose specific phases. It is possible to study this with the multipolar treatment, so-called spherical harmonics, and you get a disposition of orientation which are preferred. And if you look at this disposition of phases, you get 12 maxima, and the 12 maxima are exactly the direction normal to the faces on which this lies. So this is obtained from small angle scattering. These are obtained from normal X-ray scattering, and combine it together, you get the same information about the shape of nanoparticles. The shape is obtained here before we obtain the size dispersion and the shape dispersion. So altogether, using the Debye scattering equation in a wide angle, the Debye scattering equation in the small angle, and the Rietveld refinement at with wide angle, you obtain a complete information on the morphology of this system. Altogether, of course, is matched by the fact that you have not only particles with a core, with a dense core, but you have an expansion on the surface, which was suitably interpreted by the presence of a core with some defectiveness. The last point I want to discuss again is synchrotron measurement on this kind of molecular metal frameworks, which show a gate opening effect. Without going to the discussion, I want to show you that this material from 0 bar pressure to 29 bars with high pressure and back are flexible because they expand, and the one with iron expands even more. And by removing the pressure, it can be shrunk again. So this is very important for the study for natural gas absorption and the use of hydrogen in or storage of methane in automotive. What you see here is that at low pressure, the pattern could be interpreted by the normal standard Rietveld refinement. At high pressure, you have a lot of diffuse scattering, which is given by either the effectiveness or the presence of disordered molecules like the gases which are inserted. Let me show you something important. Here you have the observed trace at the synchrotron and the calculated trace from the ideal model. You can see that the periodic crystal simulation gives the correct position. The intensities, the integrated intensity are somewhat correct, but the width of a peak is different. So the integrated intensity of 110 and the one down here match. So the area under this peak and under this peak are correct, but this peak is broadened while the 400 is not. The 111 is very broadened. So why this happens? You have an anisotropic peak broadening, which does not depend on the length of Q, which is moving horizontally on the scale, is not depending in a vectorial way on the Q value, that means on the indices here, but should be related to a coordination geometry, which is somewhat flexible. We need then to develop a model for this system. So that means that we have position of atoms which are different than the ideal crystal, but also correlated. So then there is not a random distribution of fluctuation, but you have a so-called paracrystalline model. I will try to show you what the paracrystalline model is by taking this kind of square. If I pull this atom on one side, so I pull let's say the red one inside, the next one may move a little bit. If it moves by the same quantity, then the correlation is 1. If it moves by something less, the correlation is less than 1. If it moves counterwards, the position is negative. Of course, if I pull in one direction, could be also an influence of a neighboring row. And if I pull this one in this direction, you may have a transversal correlation in this sense. So if I pull one thing in one direction, I may have a consequence of the next neighbors along the direction, which is longitudinal, or a consequence in the transversal. Things are more complicated if you have a two-dimensional paracrystalline system, because if I pull horizontally, then I may have some shift here horizontally and some shift also on the upper layer. But if I pull vertically, then I may have some shift longitudinal for the same direction also here. So you have 4 parameters, and I have a 5th parameter, which is a correlation and a correlation angle between these two systems. So this kind of movement are they define how much one atom reflects the movement of a neighboring one. So how much correlated are the movements in 2 dimensions. So it's possible to define a probability of a certain distance, which is not anymore a Gaussian system, which would be without this term, but these are the RS longitudinal and the vertical probability, which are defined in this paracrystalline method. So there is some mathematics behind, which was included into the Debye-Scattering equation. So this is the original Debye-Scattering equation, coupled with this one makes the computation kind of a little bit more complex. And if you do this simulation, you have the original periodic crystal simulation transforms into a paracrystal simulation, and now you can check that experiment and the paracrystal simulation, they are very similar. That means that the paracrystal simulation picks up the feature which are experimentally seen. But now that we have this paracrystal simulation, can we interpret it? So if you take the original mesh, which was this kind of rhombus with all the distances, because you are filling these chains by pumping in gas, in this case methane, these chains try to enlarge, but the distances between the atoms are fixed because these morphs have a linker which are fixed in length. So what you can do is changing all this net by shifting the atoms in a way that the distance between the atoms are kept constant. So these are not random shifts, because in random shift you may have some atoms which are go farther away, some which are going closer, but the distance between these the red atoms is maintained at the expenses of different angles, which are not anymore the old ones. So I think that this is something that people have seen many times in life but never thought of. And I think that this picture gives an idea that in this net, when you have perturbation, the different meshes change shape, but more or less the length of each node-to-node distance is kept constant. So this is the paracrystalline model in real life, where the distortion is not at random. You have not random deviation, but the deviation are correlated because they are all constrained. So the conclusion is that the Debye-Scattering equation applied to nanocrystallography is a very powerful tool, and now we have studied so far about 20 different species in terms of nature, size, chemistry, and so on. And you can see that it can be applied to powders, colors, hybrids, and composites, and in principle also to liquid and gases. There are no constraints on periodicity. You can study the effectiveness of various kinds, twins, stacking folds, vacancies, self-realization. You can study stoichiometry, that means how the presence of vacancies, size and shape, and you can also do an isophase quantification. Of course, this work could not have been possible without the help of several funders from Italy, from Spain, from Denmark, and from a European community. And you see them there also, the name of some of the people who have been involved through the years. Of course, there were many, I could not fill them up. These are the core scientists who shared the project. And now I think that my presentation is over and I can stop sharing my screen and having questions from the audience. Thank you for your presence.
Thank you very much, Norberto. It's amazing. I'm feeling no water, no drinking water, speaking about an hour and a half and amazing slides and amazing lecture. Thank you very, very much.
I never drink water. I never drink water. It makes rust in the stomach.
Yeah, that's impressive. The rhythm, all the knowledge that you share with us, always in a very didactic way, and it's very clear. It's very simple. We have questions on the YouTube. People have a little delay on the YouTube, but I can share with you. One of the basic questions is on the origin of diffuse scattering. And Sergio Morellão asked about if diffuse scattering is not caused by lattice defects, which is different from diffraction or scattering by molecules or single unit cell. So maybe comment on that idea, because I posted the same thing that I liked in our presentation about the total scattering being about this put all together, and diffuse and Bragg contributions are basically on the same mathematical approach.
It's the same photons hitting the same material, atoms, electrons. So distinguishing Bragg versus diffuse scattering is something which is historical. Bragg only uses the integrated intensity of each single spot, forgetting about background, and this gives you the average structure, something which is periodic in space and infinite. If you take into account everything else which is below the Bragg peaks and between the Bragg peaks, then you enter the realm of material which are non-ideal. That means that they may have sizes which are not infinite, they are very small, they have vacancies, they have defects. And so if you take all together the Bragg peaks and the diffuse scattering, now that's why it's total, you get information, you can have an information of the full ensemble in your hands.
Yeah.
I read the question on my screen. I'm not sure I can use them, or you have a different priority list.
No,
but, you're the moderator.
No, that's okay. Just after Sergio also comment about the idea of definition of microstructure. Some case come confusing because engineers like to see microstructure of a different way.
Okay.
Maybe you can just comment this, and after you can answer Fabio, please.
No, I answer soon. Right now the microstructure. So the structure, the crystal structure we're talking about, is structure on the angstrom and nanometer level. So the crystal structure are structure at the nano size level. So the structure, but the crystals are infinite. Microstructure means something which is on a micrometer level. So it means what is happening at the higher level than bond distances. So normally microstructure is associated to shape, to size, and to defectiveness of materials. So it's not infinite crystal, it's not the nano distances within atoms, but it's something which is happening between the nano regime and the centimeter regime, say. So everything which is below the millimeter or the micrometer, it becomes micro. Micro as micrometer. This is so. If you have a size material which is below 1 micrometer, you probably see its effect on X-ray pattern. The microstructure is bigger than structure. Structure is something which is atomic structure. So there's something which is difficult to understand, because micro, one thing is smaller things. In our case, microstructure, it is a larger scale than the atomic structure. Okay, I see now Fabio. Okay, I give priority to him. How my method differentiates from PDF? So PDF takes the full pattern, removes the background, cleans it by some numerical tricks, makes a Fourier transform, and has a powder diffraction or by pair distribution function in real space. And you interpret this pair distribution function with distances. Normally, the amount of data which you collect enables you to have the the R space going from 0 to say 20, 30 angstroms. That means you can see things at a very local range, but you don't see effects which are beyond. Powder diffraction has been used in many cases. Nowadays, there are also tentatives to make 3D PDF from single crystal data. The single crystal data, if used for PDF, they are historically called Patterson function. For those who have studied this in the past, they know that the Patterson function is the Fourier transform of intensities and give you the interatomic distances. This is a powerful method to study, for example, splitting of distances you have in the same position, say, tellurides and sulfides, because with normal method you see a single atom midway, say, because you have the average with Bragg and Debye diffraction, and in with PDF you see a splitting because either you have one or the other one. You don't have an average atom at some distance. PDF is just the Fourier transform of the data, while the Debye is the Fourier series of the distances. So they are one the opposite of the other one. A PDF works in real space, and the Debye scattering equation works in reciprocal space. One of the major difficulties to get real space data is that the Fourier transform you make from the measured data to real space depend on the extent of the measurement Q you have, so how hard was the radiation you do, because there are truncation errors, and also on the signal of the noise. So every time you do some mathematical transformation on measured data, you induce an error. What we do in our modeling is that we keep the original data as they were measured. We do not touch them. We just put, say, errors or changes in our models. One thing that I have not mentioned is that in our modeling, we also introduce incoherent scattering, that is Compton scattering. Compton scattering is the portion which is scattered by electrons when they are hit by a wavelength, by a photon with a certain wavelength, and some momentum is lost. The Compton scattering you probably studied in first class of physics. And so this is also introduced in the Debye equation as additional term, and the original data are never touched, they are never transformed, these are kept as measured. So everything else comes into your model. That's, I think, is an advantage. Now I see, I had many questions. Let me see who comes first.
Marcelo Malaguti.
Malaguti. Okay. Hi, Marcelo. I had the occasion of meeting him in the past. The different shape is only cause of mismatch. No, there are other microstructure effects. For example, if you have, as I mentioned, the upper shell of a material which is a little bit stretched compared to the inner cell, like a gravity effect, so to say, then you have the distances on the top shell which are larger than inner one. So this changes significantly the pattern because a few peaks are shifted away from the regional. So it's possible to have a core shell system. If it's the same material on the surface, then inside it's called a homocore shell. If it's covered by different material, there are some technological steps in producing displays for TV, for PC and so on, which are using zinc sulfide covered by cadmium selenide or so on. You have core shell system, then a mismatch between the two different lattices may induce some differences in position, and this can be modeled. Of course, it's not derived from the data. You must build models and find out which one best fits the data. So there is also a creativity step which tells you in which direction to go to obtain your best fit. Because you are building model and you are relying on that which better explains the data. Okay? I hope I answered this question. I go to the next one.
Yeah, Cristiana Rodella is a serious science or synchrotron at Campinas, that is São Paulo State, just to but she put some news about the new beam lines.
I'm very happy to have a serious scientist, not a funny one. So, and I know the serious is just going towards the second power diffraction beam line. The important parameter to have high quality data are having a detector extending to high angles, and having the detector far enough so that you have pixel sizes which give you many data points. For PDF, normally people want to have the detector very close to the capillary, so that have flat detector measuring a large Q angles. We normally use a banana detector at the synchrotron. You might see this is called methane. I may send you the information how it's done. It covers
just
at the same time.
to interrupt you, sorry about that. Do you have a methane at this LNLS? And probably we'll put that series just to. Okay,
very good. The methane is working very fine. And we normally do 4 measurements per sample. Let me explain. You have normally the capillary filled by your, say, dry powder. You measure this. This is your measurement. Then you measure the empty capillary. Then you measure the empty space by removing the capillary itself. And then you measure the transmission of your sample in radiographic method. So basically going on 0 angle, putting some filters because you don't want to burn your material. So the transmission sample gives you an efficient absorption coefficient. It's exactly what you have in your material. So it gives you a mu factor measured. The mu factor then is applied to the sample, to the capillary, and the air. So there is a complex interplay between all these 4 measurements, which give you the total scattering, which is the real scattering from a sample once is cleaned by the air, once is cleaned by the sample holder, and by electronic effects. Cleaned doesn't mean subtracted, because when you have the capillary, the diffraction of the capillary filled and empty is different, because depends on absorption and attenuation by the sample. So there is a X-ray tracing program which was developed at the SLS, which is used for cleaning and obtaining total scattering data free of background, so everything belongs to the sample, by subtracting. I use this term subtracting, but it's not subtracting, it's computing a scattering of a glass once it is filled by a sample in the absence of the sample. So there is a strange situation that the capillary and even air scatter different, because when you have an absorbent material, the quantity of the beam which is passing through the capillary gives either fluorescence or absorption and so on, and modifies also the air scattering. So there is a mathematics which we developed, and which is simple. You can do it in one evening on your couch, but then you have to code it and to make the X-ray tracing program to correct it. So 4 measurements per sample.
It's more think about the practice than the equipment and then the stuff. You know,
yes. So the equipment you're using is fine. The important should be that if you use hard X-rays, the methane should not be transparent to this X-ray. So sometimes the methane is sold with 1, 2, or 3 layers. 2 layers of silicon are necessary to catch all the beam which is scattered, because it's very intense. So this must be specific methane.
Amazing. So maybe you can follow to the second question of Cristiani Rodella about the catalysts.
Yes.
If the metallic
single atom catalyst, let me explain. It means that, say, palladium supported on silica, on alumina. Is that what I intend? If so, we done it. We have paper.
I'm not sure if I can give you this feedback because Cristiani is at YouTube. There's a little delay. Maybe if she put some specification, but I think that's in general. She works a lot of people do catalysis. And maybe for general
absolutely possible. The problem is what is the scattering of the matrix. If you have alumina, magnesium, so okay, so you must measure this also accurately and use it as a further correction. So at that case, in that point, you must measure 5 things. You must measure the material which has the matrix and the palladium, say, or the platinum.
So as much contrast you have from the matrix and the particles.
Yes. So that means that what I mentioned by subtracting, as I said, is not subtracting. You need to correct every term to be subtracted by the absorption coefficient, which is angle dependent. So, but in principle, it will be done. If you look in in one of my slides, or I can send them to I have mentioned the case of supported platinum and palladium mixed metal catalyst on alumina. There might be a problem on the fact that some oxides are very sensitive to environmental changes. For example, if you to make platinum palladium, you normally use hydrogen as a reductant, and alumina can change its phase by treating them with hydrogen. So the alumina you use with platinum palladium is not the same as you inserted origin. So you must treat the matrix exactly as if you had the catalyst, even though there is no meaning to have it done. So you must have the same matrix as in your sample, and your sample may have changed the original material. Now, okay, Cristiano Della, a very small particle dispersed. Yes, the answer is yes. I can give you some example.
Great. Maybe you can have a last question for Sergio Morelhão at YouTube also.
Okay. You have calculated. Can I ask you what is calculated XRD? You can calculate the XRD for any shape. What is the measure?
Yeah, maybe there is a delay between the transmission at YouTube, but anyway, I think that's in general. It's again a comparison of between PDF and what you can do with Debussy, more optimistic. I have some question about what are you feeling about the future of the Debussy pair diffraction analysis? Also demands a lot of computation, but we feel, and I think that Marcel agree, that the computational part of the Debussy, it's a hard task. You have some limitations on the calculations that they use. You think that in the future, new computers, faster computers, as
I think that we are thinking of parallelizing Debussy, because many things are independent one from the other. And so the idea, if you use a 64-course procedure, then you have servers or so, and you can have parallelization of the system, and every core is doing his own job and sending back feedback. So this could speed up things. And I think that the computer will become cheaper and cheaper, or faster and faster in time in the use. But I think that if you use small enough materials, then Debussy is fast. If you use 3 nanometer particles, Debussy runs in 5 minutes on your PC. And I think that the power of this method is not for defective materials only, but particularly for nano-sized powder, where the shape of peaks is so broad that you cannot do any refit. So the power is in the less than 10 nanometer shaped materials. So I would never suggest Debussy for a normal ritual refinement. It's crazy.
Okay, and mixer phases, and we know exactly. But sorry, Fabio, I think that's Fabio Furlan from UFABC. Okay. It's asking about how to introduce stacking faults. It's
done in the past, and done. And we are still working it. Again, I can give you 3 or 4 examples. One is on one of the catalysts, the palladium catalyst. The other ones, I showed something before on the stacking fault on cesium lead bromide. We have a stacking fault on zinc oxide just published in Journal of Physical Chem. And we have stacking fault on cadmium selenide. So as long as you define your sequence, then you can just use you can have curved crystals. Why not? You can just, the point is that do you trust your model? Depends how good it fits the other data and the original data. If I can tell you that if you want to contact me for having references, just send it to me and I will send something. There are a couple of chapters in books which are also useful, and then maybe these are the best things to start with because you have already many references in this. We have written chapters, and from there you start to scientific literature.
So I think that's just to complement Sergio Morellion complement that he did just a simulation.
Okay, simulation we can also do. Simulation by simulation takes the same time. The point is that by PDF you normally do not take into account size, or if you take it, it's a single size. You do not take into account population or shapes. The Fourier transform at PDF does not take into account shape of crystals because you only look at local distance. So whether you are 1, 2, 3, or 4 nanometers away does not depend on the shape of crystals.
So I think you are finished. Thank you very much. You have a lot of questions. The audience, the attendants are very participative. It's amazing. I like it very much. It's nice.
Okay, please tell everybody that they can contact me by email, and I will be more than happy to send them something. And when I'm back to Florianopolis, I hope to share caipirinha really with you.
Oh yes, for sure. Thank you very much.
Whenever will be possible.
Yeah, thank you very much again. It's amazing, and see you soon. Take
care.
Thank you very much. Bye. Thank you all. Thank you. Obrigado, Antônio. Acho que é isso. Então, encerramos.
Sim, vou encerrar a gravação. Viu, pessoal?